Okay, today's bonus lecture is going to be at first sight it seems to be a continuation of prediction intervals, but actually I'm going to only talk about prediction intervals as a good example of the topic that I'm going to be talking about. So it seems like a natural extension. The actual topic that I would like to talk about is the total expectation. Let me write them here. And total variance rules. Total expectation and total variance rules. They are similar in nature. Variance. They are the idea or the philosophy behind them are similar. Basically, they are as you are going to as I'm going to try to show you. They are going to be determined by conditioning a random variable to another one. So since actually I said that there's going to be a conditioning of random variable to another one, we have at least two random variables here. So x and y are jointly distributed, let's say. So the total expectation rule is actually, well, before maybe going into total expectation rule, I'd like to talk about, as a transition to total expectation rule, I'd like to talk about this concept. Expected value of y given some x value. Now, this is going to be, well, actually, we can go back to chapter 5 about that. You can see the equations related with that. Well, if you have a discrete y and x, we know that f, this is going to be actually equal to fx, you can write this, fy given x value, that's specific x. So let's give a value of x0 here to show that a specific value of x is given. Y, we multiply these y values and add over domain of y. So again, I repeat, a specific value of x0 is given. When you give that value, there's going to be a conditional distribution of y over that x0 value. So we multiply each y value with the corresponding conditional probability mass function, density function, and we sum and we obtain this expected value. So this result is going to be a numerical result. Maybe you could have said, what else could have been? Now here is another expression I would like to write. Similar, but not exactly the same. Expected value of y given x. Now, what does this mean? Note that here x is a random variable itself. It is not a given quantity. So here the idea is this: given any possible x value, what would be the expected value of y? Since a specific value here is not given, note that this is going to be a specific value. This is a random variable, any value of x. This is the difference between them, a specific value of x, such that x is equal to x0. On the other hand, I leave here x as the random variable, and I repeat again, it means what is the expected value of y given any value of x. Now, in most cases, note that this is going to be a function of x. Why? Let's think about two correlated or jointly distributed random variables, such as temperature of the surroundings and let's say the spreading rate of a virus. So temperature of surroundings would be x and spreading rate of the virus would be y. The first condition would be what is the expected rate of spread rate of virus given that temperature outside is 32 Celsius. So this is going to be this expected rate at 35 Celsius is going to be a numerical result. The second one, on the other hand, is going to be a different question. It asks, what is the expected value of y? What is the expected rate of spreading of the disease given any value of surroundings? So, for instance, when temperature is equal to, let's say, 32 Celsius, that rate, whatever the unit is equal to 1.2, let's say. So think about that way. When x is equal to 32, we have 1.2 here, whatever that corresponds to. Now, when it is, let's say, 34, then the rate is equal to 1.3, let's say. And that's 30, let's say, then it's going to be equal to 0.9. So what I'm trying to say that this rate here is going to depend on this x value. So this expected value of y given x will be a function of x. I can write it that way. Actually, in the linear regression chapter, we are going to talk about that. So I'm going to again give a link to that chapter, to those lectures, so that you can see the link here. So what I'm trying to say is that now there's a very small change in the nomenclature or in the terms, but there's a vast difference in meaning. So actually, I'm going to do something else. Since this x is itself a random variable, right here, I'm going to, I have skipped one step. So since x here is a random variable itself, and this is going to be actually a function of a random variable, this quantity itself will also be a random variable. So the very important difference, this is going to be a constant numerical result, right? Whereas this is going to be a function of x, an explicit function of x. And since x is a random variable, this quantity itself will be also a random variable. So here is the interesting thing. Since this is a random variable, I can take the expected value of that random variable again. When I do that, the result is going to be the expected value of y. So again, the very interesting thing, I have used expected variable operator 2 times. So this first one is an expectation of y over a specific value of x, but that specific value is not given. So it's going to be over each of these x values. So to distinguish between this case, that specific value is given. Here, this specific value may be any value in the domain of x. So the first expectation operator is an expectation over y. If you like, you can show it in this way. Expectation over a domain of y given x values. The second, so this is going to be a function of x. The second expectation is going to be an expectation over x. Well, we don't usually show it in this manner unless in statistical learning we do that. But still, this part, actually, you don't need to use this. This expression itself is pretty much sufficient to explain this idea. So that is what we call total expectation. So basically what we do is, if we have at least 2 random variables join the distributed, we condition one random variable to the other one. We take the expected value. When we do that, the result is still a random variable. So we take the expected value again, and we determine the expected value of y. Now, can we do it for the first case? Actually, yes, you can, but it's going to be meaningless because expected value of y given x0 is already a numerical constant. Note that that may seem strange, but when you do that, the result is not equal to expected value of y. It's going to be still equal to expected value of y given x0, because this is going to be just a number here. If when you take the expected value, since this is a random variable, the second expectation operator will not have any effect here. So that they may seem subtle, but that's a very important detail, like many of the things in life or in engineering science, whatever. So this is the total expectation rule. How do we use it? Or maybe this is not very clear, the idea at this point. It may not be very clear. I'll come to that in the application to the prediction interval case. Now, when it comes to variance, a similar, if I can find the cursor, a similar equation we have here. Variance of y without any proof, I'm going to be showing, can be written in this form. Again, note that both y and x are random variable notations. Okay. So the total variance, rule of total variance is variance of y can be, if you would like to write it. At this point, one may ask, why do I bother with these complicated equations? And why don't I find y variance of y directly or expectation of y directly? One may say that. in some questions, I'm not going to go into topic, maybe in another bonus video. I don't know. But in some questions, it is difficult to determine the expected value of a random variable directly, especially if there are more than one random variable. This can be a little bit difficult. So in those cases, using total expectation and total variance rules makes the calculations easier to handle. So this is not, these equations are not to make life much more complicated, but actually much more easier. As I said, conditioning to another variable makes it easier to see what's going on. Well, the meaning of this, I'm going to talk about the meaning of this equation, these two terms on the application of prediction interval. Now, let's go into the prediction interval. Let's return to prediction interval example. Now, in prediction interval example, if you can recall, we had a population here. From that population, we had a sample X here, right? From that sample, we determine X bar value, and we determine the sample standard deviation. Then we are interested from this the same population when we are going to sample an independent observation called Y. Then what is going to be the distance or the deviation of this Y from X bar value? That was the idea. And I said that this is usually the fundamental philosophy here is very frequently used in the so-called controlled charts. In controlled charts, we first take a sample that refers to in control phase of a process. From that or from those samples, we determine the location and the spread of the process data, that in control data. Then from that, but then when the future values come, we would like to see where these new future values fall into corresponding to this X bar and S values. And I have come with some statistic, and I said that expected value of D is actually equal to 0, I said, and variance of D is equal to sigma square 1 plus 1 over n. These were the results. Now, from this perspective here that I talk about, this perspective, total expectation and total variance. Now, actually, you should realize that there are, of course, it's very obvious that there are two random variables, but there are also two different processes here. So when I talk about expectation, now one should need to think about a little bit more detail which process or which processes I am talking about. What do I mean by that? Now, when I talk about expectation, usually it's easier to think of, or distribution is usually easier to think of the frequency interpretation. If I repeat this experiment an infinite number of times, what are going to be the limiting frequencies? I should also add here that D is going to be normal distributed with 0 mean and sigma square 1 plus 1 over n. All right, now here is the question. What I call D as the deviation from, yeah, I have defined it here. Now, what does this D correspond to, or in physical terms, is an experiment itself, what is the thing that is normal distributed? So let me try to make it clear again. Is it I take a single sample X, I find X bar and S values, then I take infinite number of future observations? Is this that distribution? Or I take an infinite number of these X values, I determine X bar and S values, then I take a single sample and see where this falls. Well, actually, maybe that experiment wasn't very clear, but actually it is incorrect. Well, the correct thing is this. I take a single sample here of these n observations. I determine an X bar and S value. Then I take another Y value here, the future Y value, independent of this, a single one, a single observation, and I determine this, the distance, the deviation from X bar value. It is this distribution. So once I determine a D1 here by applying X1 and Y1, X1 after Y1, I obtain D1. Then I take another x2, another y2. Let me, maybe not, arrow is not the correct thing here. Anyway, I obtained another d2, and I take many of these samples, yn, dn, as n goes to infinity. The distribution of these d will be like that, and the expected value of d will be equal to this, and variance of d is going to be equal to this. Note that these are total expectation and total variance values. So what I mean is this: it is not I take a single sample here and obtain x bar and s here, then I take different y values and consider where these y values fall by when I transform it to d. Now, one may ask, why am I bothered? Well, okay, that may seem, maybe that's something you haven't thought about, or maybe that's something you have thought about previously. But you say, what's the big deal? What's the importance of taking a single sample than taking the consecutive y values? Again, why am I bothered with that specific experiment? Because usually that specific experiment is going to correspond to the real practice or the actual practice of control charts or process statistical process control. Why? Because in reality, if you are running, for instance, a hospital, let's say, and you are interested in the number of patients that have been accepted to the hospital in weekly periods, then what you do is you are going to take some samples from your historical data, depending on your these number of patients at various weeks. And I'm not going to go into that detail, at least in this video, how to do that. But we are going to be using this data, historical data, that is supposed to be to represent the in control status of our hospital processing or working. We are going to be determining x bar and s values, and these are going to be our mu hat and standard deviation hat values. Then from now on, once we obtain these values, as these are going to correspond to our estimated process parameters, I may say, or the estimated nominal values of our working conditions. And from now on, from on week basis, we are going to be taking the number of patients within that week, the number of patients within the next week. We are going to be taking samples and calculating the future statistics one by one. And then we are going to take these future statistics, call them y1, y2, y3, and we are going to project them on this already found, but only once found the values, right? Because these are going to correspond to our estimations of our nominal operating conditions. So we ask the question, is our current operating condition consistent with our nominal operating condition? So this is going to be the strategy that we are going to be using. Therefore, here, the statistic that we are interested in is not this one. Or maybe it's going to be this one. Actually, it's not this one. But the point is, what this statistic corresponds to, the distribution corresponds to, does not or is not equal to the story or the experiment that has been conducted here. In this experiment, a single x bar s determination, but then maybe an infinite number of y values are going to be observed. Of course, in practice, from time to time, we update these parameters, but that's out of the scope of this. Even this bonus video is going to be a further bonus video to talk about that. Actually, that's an interesting research area that's pretty much hot in statistical process control nowadays. Anyway, so a single training data or a single x bar s determination, but many future values. Now, at this point, I would like to try to solve two questions in a very similar way to what I've done here. So I'm going to consider the lowercase x value and the uppercase x value and see what is going to be the difference. So the uppercase x values, I would like to determine what is the expected value of the given x bar. And I would like to also determine what's the expected value of the given lowercase x bar. So first, let me try to determine this, because it's going to be, instead of the, I'm going to be writing y x bar minus expected value of x bar given x bar. Now, what this corresponds to, because now it's very easy to be lost in the lowercase and uppercase letters, it means that a specific value of x is given. In this case, what's the value of expected value of bar? Now, since y and x are totally unrelated, we don't care about whatever the x bar value is given. The expected value is going to be equal to mu. Now here, the x bar itself is given. What is the expected value of x bar? Note that this is the value, this is the numerical value. So it's not a statistical variable anymore. And since it is given, it's going to be equal to x bar. So here is the very interesting thing. Expected value of deviation from x bar value for a future observation is going to be equal to mu minus x bar x. And this is going to be the given x bar value from the first sample. So here, expected value of y given x bar is this, y is irrespective of the value of x, this is going to be equal to mu. So expected value of x bar given x bar is going to be itself x bar in the random variable. Now that's an important thing, and this is a distinction between those two. Here this is going to be just the computed value, whereas it's going to be still a random variable. So if you take the expectation operator once more, if you apply the expectation operator once more here, it's going to be mu minus the expected value of x bar is going to be mu, therefore is going to be equal to 0. So this is going to be what expected value of d. And actually here, without maybe paying too much attention or without realizing, we have used the total probability, total expectation, log here. As we can see, these two equations are identical. To determine the expected value of y, we condition on x and we take the expected value twice. And that's exactly what we do here. To determine the expected value of d, we condition on x bar and we take the expectation twice. We didn't find the expected value of d by this method, but actually using this method, you can much more easily, once you absorb the idea, you can much more easily follow the procedure, because there are two random experiments here. On the other hand, if you just go through the first experiment, first step once, and if the expectation operator then will apply to the second step, this is the expectation operator of the corresponding statistic. The next step is to determine the variance of this quantity. Variance of d x bar. Variance of the x bar is, using again the definition of y, is going to be y x bar plus variance of x bar, and since d is equal to y minus x bar, if we go back here, note that now I'm using lower case x bar here to denote a specific value of x bar. Is going to be 2 minus covariance y x bar. Okay, this is going to be simply equal to 0 because y is not related to the random variable. Y is not related to x bar value, so it is going to have a 0 covariance. And this one is given a specific value. What's the variance of that specific value? Is going to be again 0. And given a specific value of x bar, the variance of y again will not depend on that, and this is going to be simply equal to variance of y itself, right? So variance of y will be simply equal to sigma square. So this is going to be dx. And now here is the final. When we actually here, when we have defined d to be equal to y minus x bar in lowercase, then we have this corresponding expectation value and the variance value. And note that since x bar is any numerical value and y is normal distributed, d will be also normal distributed with mu minus x bar and sigma square. And note that this is, well, maybe we should write it a little bit different, d depending on x bar, let me put it that way. Dx bar is going to be distributed in this manner, and note that this is pretty much different from the other distribution, which is this one. Compare it with this one. Because as I said, here D is the unconditional value where I talked about the experiment here. We conduct these experiments, one sampling, one experiment standard deviation determination, one future sample. It's going to be consisting of a single sample as a whole single experiment, and the result is going to be a single D value. And on the other hand, this one corresponds to a single determination of x bar and s and many future y values. So these many future y values, the distribution of d values will be in this manner. And the idea is, if you would like to see where the discrepancy comes from, actually once you obtain this x bar value here, actually we can see that there is no s term yet. I'll come to that. Once you obtain an x bar value from a sample of, let's say, 5 or 10 observations, it's not necessarily going to be equal to the mu value. On the other hand, what you do is you obtain this future observation and you subtract from the x bar value, hoping that this is equal to mu value, and it's going to be always from the same x bar value. But actually, there's going to be a bias which is equal to this that magnitude, a constant bias in your future calculations of the dx bar statistic. So now, again, if we refer here the previous lecture, we then come up with this statistic, which z is equal to d minus mu over standard deviation of d, or standard error of d. This is a better representation. Standard error estimate of d. That was the idea. And instead of standard deviation, standard error estimate, we used the here s squared. Therefore, this was actually a t distributed random variable, right? And t distributed random variable with n minus 1 degrees of freedom. This is how we have approached the problem. Now, the problem is pretty much different here, as you can see. Let's apply the same equation here. Let's define it z as, now instead of x bar, I'm going to be using x bar and s, because those two value statistics will be obtained from the very first sample. It's going to be a future sample value y will be subtracted from the x bar, given x bar value, again a lowercase value, is not any value, divided by standard deviation here of this term here, s. So what's going to be the distribution of this quantity? This is the question at hand, because this is going to be the statistic that we are going to be using. So what we are going to do is a similar strategy that we have followed before. We are going to add and subtract the same value here, so that it's going to be minus x bar plus mu divided by, so we add mu and subtract mu here, and we are going to this time multiply both sides, both numerator and denominator, by population standard deviation. So what we are going to have here would be population standard deviation divided by sample standard deviation times y minus mu divided by population variance. And we have here, let's see, we have mu, sorry, it's not mu, it's going to be x bar minus mu divided by s. I think that seems to be okay. Mu minus, yeah. So this is going to be, as we know, this is our z0, y minus mu over sigma square. Also, this is going to be simply z normal distributed, standard normal distributed with 0 and 1 degrees of freedom. So this is going to be a coefficient here. This is going to be another coefficient here, just scalar, just constant values. Therefore, the expected value of z x bar s is going to be equal to simply, since this expectation is equal to 0, it's going to be expectation z minus. Now note that this is a constant parameter value, and these are determined by the single sample. So it's going to be x bar minus mu, let me write it that way, plus mu minus x bar over s. So since this is equal to 0, this is mu minus x bar plus over s. And variance of z s is going to be equal to variance of these two quantities. This is simply a constant here, right? And therefore there is going to be a contribution of this variance is going to be 0. So this is going to be, since there's going to be variance here, so this is going to be s square variance of z, which is equal to 1. Therefore sigma square over s square. Therefore, let me write it here. Our statistic now that x bar s is going to be equal to, or is going to be normal distributed with mu minus x bar over s mean and sigma square over s square. Now here, what does that mean? This it seems maybe a little bit, one maybe easily lost here. It means, as I said, again, you take a single sample, and let's say that this is the actual, here the mu value, the actual population mu value. But however, what you find here as x bar is going to be somewhere here, let's say. And these are your future y values that you are going to be sampling. When you sample y1, and what you do is you calculate this quantity, y minus x bar over s. And another issue is, while let's say these are the actual, let's say, this is, let's say, the real mu plus sigma and mu minus sigma values, you are going to also commit some error during estimation of the sigma value. So let's say that it's a bit higher. Therefore, x bar plus 1 standard deviation is going to be, let's say, somewhere here. X bar plus standard deviation. And here, let's say the second one is somewhere here. X bar minus standard deviation. So when you obtain a sample, actually it's supposed to come from this distribution with the peak here. On the other hand, what you do is you subtract from x bar and you divide by s, and you obtain a random variable. This random variable is not going to have a 0 mean, and 1 standard deviation is going to have these properties. This mu minus x bar over s is actually the standardized distance here, and this is the ratio of the real population variance with respect to the determined sample variance value. And well, the practical implications of that, I'm not going to go into that, but I would like to here only to show you that the distribution of our monitored variable changes. And the last thing that I would like to talk about is the application of total variance rule here. Total variance rule that I've talked about. We may also apply the total variance rule in determining the variance of a d value. Remember, I previously found this by variance of y minus x bar, and I said this variance of y plus variance of x bar minus 2 covariance y x bar, and this is equal to 0. This is equal to sigma square plus this is equal to sigma square over n. This sigma square 1 plus 1 over n. Now, well, this is actually probably the simplest method, but in many cases it might not be that much simple. If I apply this formulation, although this looks a little bit more complicated, it's going to give us more insight about what's going on. Here, when I apply this equation, variance of D is going to be equal to the expected value of variance of D given x value is going to be here x bar I'm talking about, plus variance of expected value of D given x bar. Now, what does that mean? Let's go step by step in this equation. Given the x bar value, note that this is not a specific value, this is a random variable itself, so it may change from sample to sample. we are going to be interested in the variance of D here. So it's going to be variance of Y given X bar plus variance of X bar given X bar minus 2 covariance Y X bar given X bar again. Well, actually, this part, make it clear. This part is again equal to 0 because Y and X bar has got no relation. Now, variance of X bar given that value, variance of X bar. Note that since this value, although it's not specific to, we are not talking about specific values, since this value will be given, this one is going to have 0 variance. So this is a bit tricky to see. Note that this is not going to be equal to variance of X bar. It says given that X bar value is equal to something from the first sample that we have taken, therefore X bar value will be, since it's not going to vary from that value, so its variance is going to be equal to 0. So this is going to be only this left, this term is left here. So once we have a sample, first initial training sample, and we determine the X bar value, it's not going to have any effect on the after coming Y values. So this is going to be simply equal to variance of Y. And since variance of Y is equal to sigma squared, this first quantity here is going to be equal to, let me put it that way, sigma squared. So this first quantity actually measures, given the first initial information about the experiment, how much change are we, how much variance are we going to observe in the next experiment. This one is also has a total different meaning. Let's see what it means. Expected value of invariance operator. First, let's deal with the inside. Then I'm going to be using the variance operator. It's going to be expected value of Y given X bar minus expected value of X bar given X bar and the variance of this. All right. So expected value of Y X bar given Y, note that Y is again independent of X bar, therefore this is going to be simply equal to mu. The second quantity, expected value of X bar given X bar. This is going to be equal to again X bar itself, because once X bar is given, whatever that value here is, the same value is going to be the expected value, nothing else. When we take the variance here, mu is a constant here, it has no effect, so it's going to be variance of X bar, which is going to be sigma square over n. And here we have our second term here. And this was the first term. So what does the second part deal with? This second part actually deals with the variance between the first experiment. That's the interesting point here. This expectation operator acts on the first element, but once this is determined, note that this is going to be a function of the second variable on which condition is employed. So we are trying to find the variance here. So basically, this part is related with the part between the experiments, I may say. Variance between experiments. This part is related with variance within a single experiment. This is the important distinction between those two terms. So if you look from this perspective, and if you again divide the experiment into two phases, phase 1 here and phase 2 here, where phase 1 will correspond to the determination of X bar value and phase 2 will correspond to the monitoring of Y values. This part will be initially related with the variance in phase 2, whereas this part will be related with the variance in phase 1. Therefore, variance of D can be actually determined by also this total variance rule.